The universe, in our eyes, appears dazzling and crowded, packed with stars like a city that never sleeps. But what if I told you that beneath all that brilliance lies a fragile emptiness, a silence capable of tearing everything apart? This video promises to guide you toward that chilling question. Leave your thoughts in the comments below. Do you believe in cosmic stability or in hidden fragility? And before we go any further, we must ask the first question that opens the door to everything that follows. Is the universe truly full, or is it mostly made of emptiness? What if the most dangerous thing in the universe is not a black hole, not a supernova, not even dark energy, but the silence underneath everything we call real? We look up and we see a cosmos that feels dependable. Galaxies keep their spiral arms like old records that never stop playing. Atoms hold together with the patience of stone. Light follows rules so faithfully that we build our entire civilization on its reliability. And yet modern physics invites an unsettling possibility. What if all of this stability is not a permanent fact, but a temporary arrangement? What if reality is balanced, not on bedrock, but on something more like thin glass, strong enough to hold for unimaginable ages, yet not guaranteed forever? This is where the idea of the false vacuum enters, not as science fiction, but as a serious thought that emerges from quantum field theory and the way the Higgs field seems to behave. The word vacuum sounds like nothing, but in modern physics, vacuum means the lowest energy state available to fields that fill all of space. And fields are not optional decorations. They are the stage, the lighting, and the script at once. They decide what particles are allowed to exist, how heavy they are, how they interact, and whether chemistry can even happen. So, when we ask whether the vacuum can destroy the universe, we are really asking whether the foundational setting of those fields can change. Peter Higgs once put it with calm precision. When you look at a vacuum in a quantum theory of fields, it isn't exactly nothing. Tensory, from send. That single sentence is a doorway, because once you accept that empty space is not empty, you have to accept something else too. If the vacuum is a physical state, then it can have structure. If it has structure, it can have alternatives. And if it has alternatives, then the vacuum we live in might not be the deepest, most stable option available. Imagine, for a moment, that the universe is resting in a valley of energy. Not a valley made of dirt and rock, but a valley in an abstract landscape that describes how a field prefers to settle. If the valley we occupy is the lowest possible, then the universe is anchored. But if there exists a deeper valley somewhere else in that landscape, then our vacuum is not the true bottom. It is a local minimum, comfortable, coherent, life-friendly, yet not the final floor. That is what physicists mean by a false vacuum. It is stable the way a book is stable on a shelf. Stable, yes, but not welded to the air. Move the shelf, tilt the world, and the story can fall. Here is a simple image that makes the idea less abstract. Picture a marble sitting in a shallow dimple on a tabletop. To your eyes, it is at rest. It has found its place. Now picture that the tabletop itself hides a deeper bowl just beyond a small ridge. The marble does not know about that deeper bowl. It does not need to. As long as it stays in its shallow dimple, the world looks settled. But if there is even a tiny chance, however small, that the marble can slip through the ridge without climbing it in the normal way, then the stability you trusted is not absolute. In quantum physics, that tiny chance has a name: quantum tunneling. A system can cross barriers that would be impossible in classical physics, not by conquering the wall, but by exploiting the probabilistic nature of reality itself. Now take that marble and replace it with the vacuum state of the Higgs field. Suddenly, the question becomes enormous, because the Higgs field is not a side character. It is one of the reasons particles have mass at all. Mass is not just a number on a chart. Mass is the reason electrons can orbit nuclei in stable ways. Mass is the reason atoms have size and chemistry has rules. Mass is the reason stars can ignite and planets can form and brains can exist long enough to wonder. So if the Higgs field were to shift into a different vacuum state, the masses of fundamental particles could change. And if masses change, forces effectively change. And if forces change, the architecture of matter can collapse, not with drama and flames, but with quiet inevitability, like a melody that simply stops being playable because the instrument has changed shape. This is why the question feels so sharp. If reality is a balance, what does that say about everything we love and trust? It says that the universe might not be a fortress. It might be a phase. A long phase, a generous phase, a phase so vast that it makes human history look like a blink, but still a phase. And there is something humbling in that. Not because it is meant to frighten us, but because it reminds us that our deepest assumptions are not sacred. They are provisional. At this point, a thoughtful viewer often asks the most practical question of all. If this is real, why are we still here? The answer is that possible and likely are not the same word in physics. The calculations that come out of the Standard Model, using the measured masses of the Higgs boson and the top quark, suggest a curious result. Our vacuum may sit near a boundary, not decisively stable in the strict mathematical sense, yet so long-lived that its decay time could dwarf the age of the universe by absurd factors. That means you should not live in fear of tomorrow, but you should allow yourself to feel the philosophical weight of the idea, because it implies that the stability we experience is not guaranteed by comfort. It is earned by numbers, by parameters, by the precise values nature selected, or perhaps drifted into. To make the metastable idea feel real, consider a second example, far from particle accelerators and equations. Think about supercooled water. Water can be cooled below its normal freezing point and still remain liquid if it is undisturbed. It looks calm. It pours like ordinary water, but the state is precarious. A small shock, a vibration, even a seed crystal, can trigger a sudden transition. In an instant, the liquid reorganizes into ice, not because ice was forced upon it from outside, but because ice was always the more stable phase available. The water was simply lingering in a temporary calm. Metastability is that kind of calm. Not fake, not imaginary, but conditional. If the vacuum of our universe is metastable, then vacuum decay would be the cosmic version of that sudden transition. A tiny region of space would shift into a lower energy vacuum state. It would form what physicists describe as a bubble, not a bubble of air in water, but a bubble of altered vacuum, where the rules of fields take on new values. And because the new vacuum would be more stable, the boundary would expand outward, potentially at speeds approaching the speed of light. Everything the bubble touches would be converted, not burned, not smashed, but rewritten. Matter might not survive because matter depends on the old rules. Chemistry might not survive because chemistry depends on stable atoms. Light might not behave the same because electromagnetism depends on the structure of fields. The tragedy, if you want to call it that, is its silence. There would be no warning, because nothing can outrun the boundary if it expands at light speed. No signal arrives ahead of the change. The universe would not scream. It would simply become something else. And this is where the heart of your theme lands with full force. If reality is only a balance, what does that say about existence? It says that existence is not just a fact, but a condition maintained by the shape of an energy landscape we cannot see with our eyes. A condition protected, perhaps, by the sheer enormity of timescales, but still defined by the possibility of transition. That does not cheapen life, it dignifies it, because it means our world is not trivial. It is an arrangement so exquisitely tuned that a small change in the deep structure of fields could erase everything we recognize. And yet here we are, living inside the coherent chapter, inside the stable paragraph, inside the version of physics that allows memory and music and love and thought. There is also a deeper educational lesson hiding inside this, one that viewers in their bones can feel. Science is not only a catalogue of answers. It is a disciplined way of admitting what we do not know, while still refusing to stop asking. The false vacuum question exists because modern physics is brave enough to interrogate its own foundations. It looks at the floor beneath the universe and asks whether that floor is solid rock or a temporary platform. It takes measured numbers from experiments and follows them to their ultimate implications, even when those implications feel surreal. And it does all of this without declaring doom, because the point is not panic. The point is understanding. So the hook becomes more than a hook. It becomes an invitation to see the cosmos honestly, not as a comforting machine, not as a hostile abyss, but as a living set of possibilities constrained by mathematics and revealed by observation. And once you feel that, you start to realize why this topic grips the mind, because it is not really about destruction. It is about the shocking idea that even the nothing we ignore, the emptiness between stars, may be the most important physical substance of all. And if the vacuum can carry the universe, then the vacuum might also be capable, in principle, of changing the universe. And that brings us, naturally and inevitably, to the next door we have to open. If we want to understand whether the vacuum could ever rewrite reality, we first have to face a simpler question that most people never fully sit with. Is the universe truly full, or is it mostly made of emptiness? What if the most dangerous thing in the universe is not a black hole, not a supernova, not even the heat death of time itself, but the emptiness between atoms? What if nothing is only pretending to be quiet, while underneath it, reality is balancing on the edge of a deeper state it could fall into? Physicists call this idea vacuum decay. And the name sounds like rust, like erosion, like something slow and visible. But that is not what makes it haunting. What makes it haunting is the possibility that it would not arrive like a disaster you can watch coming. It would arrive like a rule change, a silent edit to the universe's operating system. To understand why, we first have to unlearn a habit of imagination. Most of us picture space as a container, a stage, a dark room where matter is the furniture and light is the music. In that picture, the vacuum is just the empty floor between objects. But modern physics suggests a stranger image. The vacuum is not merely absence. It is a state. It has structure. It has energy. It is more like an ocean you cannot see, whose surface looks calm from far above, but whose depths are always moving. In quantum field theory, what we call particles are excitations of underlying fields, and those fields exist everywhere, even where you think there is nothing. So the vacuum is not a blank page. It is the page with ink that has not yet formed letters. And that is where the possibility of decay enters the story. A vacuum can be stable, meaning it sits at the lowest possible energy, like a ball resting at the bottom of a valley, or it can be metastable, meaning it sits in a shallow valley that looks safe, feels safe, behaves safe, but is not the deepest valley available. There could be a lower valley separated by a ridge, a barrier, a kind of energetic hill that keeps the ball trapped where it is. From a classical point of view, if the ball does not have the energy to climb the hill, it stays forever. From a quantum point of view, nature allows a loophole, a tiny probability that the ball can appear on the other side without ever climbing over. That loophole is not a metaphor, it is a real effect. And when you apply that logic not to a ball, but to the vacuum state of the universe itself, you get the unsettling idea that our vacuum could one day transition to a lower energy state. If that happens, it is not an explosion in the ordinary sense. There is no fireball expanding into pre-existing space. There is no shockwave traveling through unchanged physics. Instead, the vacuum itself changes, and because the vacuum is the stage on which all particles and forces are defined, the rules that make atoms possible could change with it. That is why people describe vacuum decay as a rewriting of physical law. It is not that matter is smashed. It is that matter may no longer be allowed to be matter. Stephen Hawking once warned, with the calm bluntness he was famous for, that a transition to a lower vacuum state could expand at the speed of light and destroy everything in its path, without warning. That single thought contains the emotional weight of the entire topic. No warning, no heroics, no last message, just the universe switching to a different version of itself. Now, does that make vacuum decay a catastrophe? Or is it a phase transition, like water freezing into ice? The honest answer is that it could be described as both, depending on where you stand. From our perspective, it would be the end of everything we recognize. From the perspective of physics, it might be nature doing what it always does, sliding toward a more stable configuration. In that sense, it resembles the transformations we already know, except unimaginably more total. When water freezes, the molecules are the same, but the pattern changes, and suddenly you have a new set of behaviors, a new world of possibilities. In vacuum decay, the molecules of reality, the fields themselves, may settle into a new pattern, and the behaviors that once held atoms together might vanish. Imagine, for a moment, a stained glass window in an old cathedral. From the outside, it looks like a single object, one grand image held in place by invisible structure. But the image exists only because every piece of glass is shaped exactly, and every lead line holds exactly. Now imagine the lead lines softening, not melting into flame, but quietly losing the property that makes them hold. The window does not explode, iduna. It simply stops being a window. The picture ceases to exist, and the pieces become meaningless fragments because the rules that gave them form have changed. And that brings us to the question that makes people uneasy. If vacuum decay occurred, what would disappear first? Matter, forces, or space itself? The best way to think about this is to remember that these categories are not as separate as our everyday language makes them seem. Matter is stable only because forces have the strengths they have. Forces have the strengths they have because the underlying fields and constants take particular values. And space-time is not merely a container in modern physics, but part of the same deep structure that defines what fields even mean. In many descriptions, what fails first is not space, but the relationships that allow stable particles to exist. Masses could change, couplings could shift. The electromagnetic force might not bind electrons to nuclei in the same way. The strong force might not hold protons and neutrons together. Chemistry, which is really the poetry of electromagnetism, could collapse in an instant. Stars would not burn out. Stoic, Isling, Stoic 5. They would become irrelevant, because the kind of matter that makes stars possible could no longer assemble. But in another sense, space itself would be altered, because space in physics is not a neutral emptiness. It is the environment defined by the vacuum state. So when the vacuum changes, the geometry and permissible excitations change with it. It is less like a bomb going off in a room, and more like the room becoming a different room before you can even realize it happened. Here is the first example, placed far from the second, so it can breathe. Think about a chessboard, not the pieces, the board. Now imagine that in the middle of a game, without touching any piece, the rules of movement change. Bishops no longer move diagonally. Kings no longer have meaning. Squares are still squares, but the logic that gave them purpose is different, and suddenly the positions that once made sense are nonsense. That is closer to the spirit of vacuum decay than any image of fire and debris. The universe does not get hit by something. The universe becomes something else. And yet, for all its drama, physics also forces humility here, because possible is not the same as likely, and terrifying is not the same as imminent. To speed today, when scientists talk about vacuum decay, they are often talking about timescales so vast they almost mock human intuition. The calculations, based on what we currently know about the Higgs field and other parameters, suggest that if our vacuum is metastable, its lifetime could be incomprehensibly long compared with the current age of the universe. That does not make the idea unimportant. It makes it more profound. It means the universe may be balanced on a knife edge that is steady enough for galaxies to form, for life to evolve, for minds to ask questions, and yet still not guaranteed in the deepest sense. This is where the educational value becomes more than facts, because the topic teaches a rare form of scientific thinking. It teaches that emptiness is an active concept. It teaches that stability can be an illusion that lasts longer than civilizations, longer than stars, longer than most of the story we can tell. And it teaches that the laws we treat as eternal might, in principle, be contingent, dependent on the state the vacuum happens to occupy. We tend to think the universe is built out of things, planets, galaxies, atoms, light. But vacuum decay asks us to consider that the universe is built out of conditions, out of an arrangement, out of a delicate agreement among fields. And if that agreement changes, even slightly, the visible world could become as impossible as a dream you can't remember. Now here is the second example, far from the first. Picture a radio tuned perfectly to a station, music playing clearly. The song feels solid, like it exists out there. By Fivers is Tubilitia. But the song is not a thing in your room. It is an interpretation produced by the tuning, by the receiver's design, by the electromagnetic environment. If the tuning changes, the music does not explode. End quote. It vanishes into static, and a different station may appear, governed by a different pattern. Our universe may be like that radio. The vacuum is the tuning, the laws are the station, and vacuum decay would be the dial slipping to a new frequency where the old song cannot be played. So is vacuum decay a threat, or is it simply the universe's right to evolve into deeper stability? That depends on whether you define the universe as the totality of existence or as the particular version of existence that allows stars, atoms, chemistry, memory, and human voices. Because vacuum decay, if it ever happens, would not necessarily end existence. It would end our edition of existence. And that, in the end, is why the idea grips the mind. Not because it invites panic, but because it invites awe. It reminds us that reality is not just vast in size, it is vast in depth. The true mystery is not only what fills the cosmos, but what the cosmos is resting on. And once you realize that the emptiness might be a living foundation, not a dead absence, you start to see the night sky differently. The stars become not only lights in space, but ornaments pinned to a fragile underlying state that makes light and space mean anything at all. So let me leave you with the question that naturally opens the door to what comes next. If vacuum decay is a story about the power of nothing, then we must first face a simpler, more unsettling truth. So let me leave you with a reflection that leads us forward. If vacuum decay is truly the story of nothing shaping everything, then the universe may not be as full as it appears. What if the emptiest place you can imagine is not empty at all? What if nothing is only the mask the universe wears when it does not want to be seen? For most of human history, the word vacuum sounded like peace, a quiet stage where matter performs, while the backdrop remains still. Classical physics encouraged that picture. Remove the air, remove the dust, remove every atom you can trap, and you should be left with pure absence, a perfect silence, a blank page. But modern physics walks into that quiet room and whispers something unsettling. Even when you take everything away, something remains, not as a leftover mistake, but as a rule, not as a technical detail, but as the deep character of reality itself. John Archibald Wheeler once said, "Empty space is not empty. It is the seat of the most violent physics." Loki noused. That single sentence is a doorway, because it suggests that the vacuum is not the absence of activity. It is activity in its most fundamental form. It is the ocean, and what we call matter is the foam. It is the instrument, and what we call particles are the notes. So what does nothing mean in modern physics? In quantum field theory, the universe is not built out of little hard beads called particles. Instead, it is woven from fields that exist everywhere, all the time. An electron is not a tiny marble flying through emptiness. It is a localized ripple in the electron field. A photon is not a bullet of light crossing a dead void. It is a ripple in the electromagnetic field. And if fields are everywhere, then the vacuum cannot be a truly empty container. The vacuum becomes the lowest energy state of those fields. Not a void, but a baseline. Not nothing, but the quietest possible something. HU. And here is where modern physics becomes almost poetic. Even the quietest state is not perfectly still, because at the quantum level, nature does not permit absolute rest. There is always uncertainty, always a faint trembling, always a subtle refusal to sit completely motionless. The vacuum, in this view, is like a dark sea at night. From a distance it looks calm and glassy, but beneath the surface, unseen currents move. Not because anyone disturbed the water, but because the water is alive with motion by its very nature. You might ask, if there are no particles, why is there energy? Because no particles is not the same as no fields. 19. And fields cannot be pinned down to zero, everywhere, forever. If you try to force them into perfect stillness, quantum uncertainty pushes back. So the vacuum holds what physicists call fluctuations, tiny, momentary variations in the fields. Not full-fledged particles you can bottle and keep, but brief stirrings that can leave measurable fingerprints. This is the part that changes the meaning of reality. because it says that emptiness has structure. It says that silence has texture. It says that nothing can do work. Imagine two perfectly smooth metal plates placed extremely close together in a vacuum. No air between them, no dust, no hidden gas, just emptiness. Classically, nothing should happen. And yet, in the real universe, there is a faint force drawing those plates together. The vacuum, acting like an invisible hand, produces pressure. It is not magic. It is not a trick. It is a consequence of what kinds of quantum fluctuations are allowed in the narrow space between the plates versus outside them. The difference creates a net push, like a tide you cannot see but cannot deny. This is one reason modern physicists hesitate to call the vacuum nothing. It's Spencer, because nothing, if it can push, is not nothing in the ordinary sense. Now, if we step back and look at the bigger picture, a deeper question appears. Is the vacuum the foundation of matter, or is it only an illusion created by old-fashioned intuition? The honest answer is that our intuition evolved for stones, wind, water, and fire. It evolved for a world where emptiness meant there was simply less stuff. But the quantum world is not obligated to make sense to the instincts of an ape on a small planet. Our classical perception treats space like a box and matter like objects inside it. Quantum physics flips the story. It suggests matter is what space can do when its fields are excited. It suggests particles are not the occupants of reality, but the behaviors of reality. In that sense, the vacuum is not an empty room waiting for furniture. It is the house itself, with hidden wiring humming behind the walls. And that hum is not just a curiosity. It reaches into the very stability of the world. Atoms, for instance, are not little solar systems made of rigid parts. They are quantum structures held together by rules that do not behave like everyday mechanics. Even the way electrons sit around a nucleus is shaped by quantum fields and their restless baseline energy. When physicists measure certain tiny shifts in atomic energy levels, they find the signature of the vacuum's activity. The atom is not floating in emptiness. It is immersed in a sea that subtly changes its behavior. This leads to a strange kind of humility. We used to think the universe was made of things, plus empty space between things. Now we suspect the universe is made of fields, and things are just the bright crests of those fields. The vacuum is not the pause between notes. It is the instrument still vibrating after the music stops. At this point, it is tempting to ask whether the vacuum is dangerous. Not because it feels threatening day to day, but because it reframes what stable even means. If the vacuum is an energetic state, then it can have different levels, different configurations, different depths. And that is where the famous idea of a false vacuum enters the imagination of physics. A state that looks stable, behaves stable, lasts for eons, yet is not the deepest possible stability. Like a marble resting in a shallow dip on a mountainside. It can sit there for 1,000,000 years and look perfectly safe, but the landscape beneath it still contains a lower valley. And if the marble ever transitions, everything about its environment changes. Notice how this alters the emotional meaning of nothing. Dodations, and defiances. The vacuum is no longer a passive absence. It becomes an active participant. It becomes a stage that can rewrite the play. It becomes the background that can, under rare conditions, become the main event. Here is a second way to picture it, far from metal plates and laboratory setups. Think of the vacuum like the silence inside a vast cathedral. You step in and feel stillness, but the air is not truly still, and the building is not truly silent. Tiny vibrations travel through stone, Microscopic motions ripple through wood and glass. Even when no choir is singing, the architecture holds tension and resonance. Now imagine that the cathedral's silence is not just a lack of sound, but a physical state the building must maintain. A state with a certain energy, a state that can shift if the conditions change. That is closer to the modern idea of vacuum than the word nothing ever was. So, is the vacuum the foundation of matter? In many modern descriptions, yes. Not in the mystical sense that it is a magical substance, but in the precise sense that the properties of matter depend on the properties of fields, and the vacuum is the fields at their lowest energy. Change the vacuum, and you change what particles can exist. Change what forces can operate. Change what chemistry is even possible. In that sense, the vacuum is not merely where things happen. It is part of what makes things possible in the first place. And is the vacuum an illusion of classical perception? Also, yes, in a different sense. Because our classical mind sees emptiness as the absence of ingredients. Quantum physics asks us to see emptiness as a state with rules, constraints, and latent power. The illusion is not that the vacuum exists. The illusion is that it is inert. The illusion is that nothing cannot influence something. Is. If you carry only one idea away from this, let it be this. The vacuum is not a blank. It is a background filled with potential. It is the calm surface of a deeper storm. And the more carefully we measure reality, the more we discover that what we once dismissed as nothing may be the most important something of all. So now the curiosity becomes impossible to ignore. If the vacuum is alive with energy, if it can shape matter, if it can leave fingerprints on the world, then what does that imply about the universe we live in? Is the cosmos truly a bright, crowded place? Or is it mostly an ocean of this restless emptiness, with islands of matter floating like brief sparks in the dark? What if the thing that decides whether atoms hold together, whether stars can burn, whether chemistry can exist at all, is not a particle you can point to, but an invisible field that fills every inch of space? What if the universe is not held up by pillars of stone, but by a quiet, mathematical mood of emptiness itself? The Higgs field is often introduced with a comfortable promise. It gives particles mass. It makes the universe feel solid instead of ghostly. And that is true, but it is also only the first page of a longer, stranger story. Because the deeper role of the Higgs field is not merely to add weight to matter. Its deeper role is to help define the vacuum, the baseline state of reality, the ground level upon which every law of physics stands. And once you grasp that, the question changes. We stop asking, what does the Higgs do to particles? And we start asking, what does the Higgs do to existence? Say please. Picture it this way. Space is not an empty container. Space is more like an ocean whose surface looks calm from far away, but whose depths are alive with currents, pressure, and hidden structure. The Higgs field is part of that structure. It is present everywhere, even in the darkest void between galaxies. And particles moving through it are not simply moving through nothing. They are moving through a medium that can slow them down, shape their behavior, and determine what kinds of stable matter are even possible. Here is the first example, simple enough to feel in your bones. Imagine a world where everyone must cross a vast room. In one version of the room, the floor is polished ice, and everyone glides effortlessly. In another version, the room is filled waist-high with thick water, and every step becomes heavy, delayed, resisted. Nothing about the person changes. Nothing about their intention changes. What changes is the medium they move through. In the language of modern physics, the Higgs field is that unseen medium. Different particles feel it differently. Some barely notice it and remain light. Others interact strongly and become heavy. Mass, in this view, is not just a property of an object. It is a relationship with an all-pervading field. But the most unsettling part is what comes next. Because the Higgs field does not only set masses, it also participates in shaping the energy landscape of the vacuum itself. And vacuum, in quantum physics, is not a synonym for emptiness. It is the lowest energy state available to the fields that fill the universe. It is the default setting of reality. When fields settle into certain values, the laws of nature take on their familiar form. Electrons behave like electrons. Light behaves like light. Nuclei bind. Chemistry ignites. Stars kindle. Life becomes possible. This is not poetry. It is structure. The universe is not only made of things. It is made of rules, and rules are made of fields. So what happens if the Higgs field were to change its state? Not a small fluctuation like the jitter of a needle, but a true shift, a fall into a different valley of its energy landscape. In that case, the vacuum itself would be redefined. And if the vacuum is redefined, then the masses of fundamental particles can change. The strengths of forces can change. Even the stability of atoms can change. The periodic table, that quiet scripture of chemistry, could become meaningless. Stars might fail to fuse, or fuse too fast, or never form stable nuclei at all. The same universe, the same space, the same stage, but a different script, and therefore a different reality. This is why physicists sometimes speak, carefully, about vacuum stability and metastability. Those are calm words, almost polite, but the idea behind them is dramatic. It suggests that our universe may be resting in a state that is stable for an unimaginably long time, yet not guaranteed to be the deepest possible state. Like a marble sitting in a shallow dip on a mountainside, it can remain there for ages. It can look perfectly secure, but somewhere beyond the ridge there may be a deeper valley, a lower energy truth. If the marble ever tunnels through the ridge by a quantum process, it would roll into that deeper valley and never return. And because fields define the vacuum, this would not be a local accident. It would be a fundamental rewrite. As physicist Brian Greene once put it, the Higgs field is like a kind of cosmic molasses that fills all of space. Is chanting. That image is famous because it helps the mind hold on to something invisible. But there is another implication hiding inside the metaphor. If the molasses itself could change, thicken, thin, or settle into a different phase, then everything moving through it would change too. Not gradually, not by negotiation, but by necessity, because particles do not vote on their masses. They inherit them from the vacuum they are born into. Now, it is crucial to stay honest here. No serious scientist is telling you to panic. The best calculations we have suggest that if vacuum decay is possible, it is extraordinarily unlikely to happen any time remotely near the present era of the cosmos. The timescales often discussed are so vast they make the lifetime of stars look like a blink. But improbability is not the same as impossibility. And the educational power of this idea is not in fear. It is in perspective. It teaches us that the universe is not built like a brick house. It is built like a finely tuned instrument. Stable, yes, but stable because conditions align, because fields settle, because parameters fall into narrow windows where complexity can survive. And here is where the Higgs field becomes, quietly, one of the most important characters in the story of reality, because the measured mass of the Higgs boson, along with the properties of the heaviest known quark, hint that we might be living near a boundary. A cosmic shoreline between absolute stability and a slow drift toward instability. Not a cliff we are about to fall from, but a border that tells us something profound. That the universe may be balanced, not deep in the safest valley, but somewhere near the edge of a larger landscape we cannot yet fully map. What would change if the Higgs field changed state? Try to imagine it without Hollywood explosions. There may be no warning light in the sky, no rumble, no fireball. If a true vacuum transition occurred, it would be less like a bomb and more like a sudden change of language at the deepest level of nature. A different alphabet for matter, a different grammar for forces. The equations that define electrons, photons, and quarks would no longer describe the world inside the new vacuum in the same way. And because the laws would change, the structures that depend on them would fail to persist. Atoms might not be atoms. Light might not propagate with the same character. The concept of solid might not exist. And the strangest part is that this would not be the end of everything in an absolute sense. It would be the end of our version of everything. If that sounds almost philosophical, it is because physics at this depth naturally becomes philosophical, not by preaching, not by mysticism, but because once you see that reality depends on the state of fields, you realize how contingent the familiar world may be. We tend to believe that the laws of nature are eternal, but the Higgs story whispers another possibility, that what we call the laws may be the outcome of a particular vacuum state, a particular configuration, a particular settling of the universe into a workable arrangement. And if that is true, then the real mystery is not only what exists, but why this set of rules, why this stable pattern, why this delicate balance that allows stars, chemistry, memory, and mind. Much later in the story, you can return to a second example, and it lands differently once you have absorbed the stakes. Think of an old radio, the kind with a smooth dial you turn by hand. At one position you hear music, clear and coherent. Move the dial slightly, and the music fades into static. Keep turning, and another station appears. Different voices, different language, different world. The radio has not changed. The air around it has not changed. What changed is the tuning, the hidden alignment that decides what signal becomes reality in your speaker. In a rough, imperfect way, the vacuum state plays a similar role for the universe. The Higgs field helps set the tuning, and the world we live in, with its atoms and stars and fragile lives, is the station that comes through when the tuning lands where it does. So why does an invisible field control the structure of all reality? Because in modern physics, invisibility is not weakness. It is foundational. Gravity is invisible too, yet it shapes galaxies. Time is intangible, yet it rules every heartbeat. The Higgs field belongs to that deeper category. It is not a thing sitting inside the universe like a planet or a star. It is part of what the universe is made of, part of the fabric that decides which forms of matter can exist and which cannot. And once you accept that, you begin to sense the real educational gift of this topic. It trains the mind to see beyond objects, beyond surfaces, beyond the temptation to think reality is only what you can hold. Because the universe is not only a collection of things, it is a choreography of fields, and the Higgs field is one of the quiet choreographers, shaping the dance so thoroughly that we mistake the dance for inevitability. If you feel a chill at the edge of that thought, that is normal. Not because the universe is about to collapse, but because you are touching a truth the human brain rarely has to face. That existence may be a phase, a configuration, a settled state, a delicate harmony that can be described with mathematics, tested with experiments, and still remain mysterious in its ultimate meaning. And the next step is to ask the question that naturally follows from everything we have just explored. If the Higgs field helps define the vacuum, and the vacuum may not be the lowest possible state, then how do we test the stability of our cosmic ground? How do experiments, particle colliders, and cosmological observations let us measure the tuning of reality itself? That is where the story goes next. What if the universe is not sitting safely in the valley of reality, but balancing on a thin ridge where one step in the wrong direction rewrites everything? That single question is why the Higgs boson and the top quark matter far beyond particle physics, because together they whisper something unsettling about the stability of the vacuum itself. In modern quantum field theory, the vacuum is not a blank stage waiting for matter to enter. It is the stage, the lighting, the floorboards, and the hidden machinery underneath, all humming even when no actors appear. Frank Wilczek once captured this with a line that still lands like a quiet thunderclap. The vacuum is not empty, it is full of energy. It isn't. If that is true, then the vacuum is not merely where the universe happens, it is what the universe is made of at its most fundamental level. Now here is where the story turns. The Higgs field, which permeates all space, sets the masses of many particles and helps determine the shape of the energy landscape that our universe rests in. When physicists combine the measured Higgs mass with the measured top quark mass, the equations suggest an eerie possibility. Our vacuum may be metastable, meaning it looks stable, behaves stable, and can remain unchanged for inconceivably long spans of time, yet it might not be the deepest possible state of reality. In other words, there may exist a lower energy vacuum state, a truer valley beneath the one we occupy, and quantum mechanics allows transitions between such states in rare, unpredictable ways. Here is a simple way to feel the idea without drowning in math. Imagine a smooth marble resting in a shallow dimple on a tabletop. It sits quietly, it does not roll away, it seems secure, and if you glance at it for a lifetime you might swear it is locked in place. But the tabletop hides a deeper hole somewhere else, and the marble is not in the deepest hole, it is only in a comfortable one. A tiny jolt, not even a dramatic shove, could in principle send it out of its shallow resting place and into the deeper basin, and once it falls there, the entire situation is permanently different. That is the emotional core of the universe near the edge. In time, not that the cosmos is about to explode like a bomb in a movie, but that reality could, in principle, have more than one resting state. The unsettling part is not the drama of destruction, it is the quietness of the mechanism, because vacuum decay is not a conventional disaster. It would be a phased change, a total redefinition of the rules, as if the operating system of existence were replaced in an instant. So why do today's measurements place us near a stability boundary? Because when the Higgs and top quark masses are plugged into the standard models running of couplings, the Higgs potential appears to sit in a shape that is neither comfortably stable nor obviously doomed. It is poised in a narrow region where the vacuum is not the absolute minimum, yet it can still survive for timescales so vast they swallow all ordinary intuition. That awkward placement is what makes physicists raise an eyebrow, because nature did not have to choose parameters that land so close to the line between stability and metastability. And this is where the question becomes more philosophical than apocalyptic. Is this nearness a coincidence, a random outcome of deeper laws we have not yet seen, or a sign that our current picture is incomplete? Some researchers treat it as a hint that new physics may exist beyond the standard model, nudging the vacuum towards safer stability. Others wonder if it reflects a deeper organizing principle, as though the universe is tuned to be just stable enough to allow complexity, but not so rigid that it cannot transform across cosmic epochs. Long before you worry about doom, it helps to understand what near the boundary does and does not mean. It does not mean tomorrow is dangerous, because even in metastable scenarios, the predicted lifetime can be staggeringly longer than the current age of the universe. It does mean, however, that the vacuum is a physical object in the most profound sense, with properties, structure, and a measurable relationship to the particles we discover. Much later in the story, after you have lived with the marble on the table image for a while, consider a second picture that lands differently. Think of a supercooled liquid, perfectly clear, perfectly calm, sitting below its normal freezing point. It looks ordinary until a single microscopic crystal forms, and then suddenly the entire liquid reorganizes as a new phase sweeps through it. No warning siren, no gradual negotiation, just a rapid transformation once the seed appears. That is closer to the spirit of vacuum decay, not an explosion, but a conversion, a change of phase, a new reality spreading from a tiny origin. So when we ask whether we live on the boundary between existence and collapse, we are really asking whether existence is one fixed arrangement or one choice among many. The Higgs and the top quark are not merely particles, they are numbers that sculpt the contours of the vacuum's energy landscape. And the fact that those numbers place us near a theoretical border is either a cosmic accident of breathtaking indifference, or a clue that we are missing a deeper layer of explanation. If the universe is a book, this is the moment we realize the page we are reading might be a page that could have been written differently. And that leads naturally to the next step, because the moment you accept that the vacuum has a structure, you must confront the simplest, strangest question of all. Is the universe truly full, or is it mostly made of emptiness? What if the universe is not held together by unbreakable laws, but by a temporary calm that could, in principle, slip? We look up at the night sky and it feels permanent. It feels like a cathedral of light built from granite and patience. Yet modern physics invites a stranger possibility. That what we call empty space is not a passive backdrop, but an active state, a kind of energetic balance sheet, and balances can, in rare cases, be rebalanced. The phrase for the most extreme version of that idea is vacuum decay. Not an explosion in the Hollywood sense, not a fireball rolling through galaxies, but a transition, a change of state where the rules governing particles and forces would be different on the other side. Here is the unsettling part. If such a transition could happen at all, what could possibly trigger it? And should we fear some cosmic domino, or even our own curiosity, pushing the first tile? Stephen Hawking once warned that the vacuum is not empty, but full of the potential of particles and forces, a reminder that the quietest-looking places in nature can hide the deepest activity. To understand triggers, you first have to picture the vacuum not as nothing, but as a landscape of possibilities. In quantum field theory, the vacuum is simply the lowest energy state available to fields, but lowest can be tricky. There may be a state that is low enough to seem stable for unimaginable spans of time, yet not the absolute lowest. That is what people mean by a false vacuum. It is like standing in a shallow valley on a foggy night, convinced you are at the bottom, when somewhere beyond the mist there might be a deeper basin you cannot see. From there, the first trigger to consider is the most eerie because it requires no external cause at all. Yes, vacuum decay could be spontaneous in principle. Quantum mechanics does not only describe what must happen, it also assigns tiny probabilities to what can happen. Even if a system lacks the energy to climb over a barrier in the classical sense, it can sometimes tunnel through, as though the barrier were briefly porous to the mathematics of possibility. If our vacuum were metastable, then somewhere, sometime, a microscopic region could tunnel into a lower energy vacuum state. That region would behave like a seed. And if the new vacuum state were truly more stable, the seed could expand, converting space as it goes. Not because it is angry or malicious, but because nature tends to roll downhill when a downhill exists. Think of a supercooled liquid that looks perfectly calm. It can sit below its freezing point, still transparent, still fluid, still innocent. Then a single tiny disturbance creates the first crystal, and once that crystal forms, the rest of the liquid reorganizes around it with startling speed. The liquid did not decide to change. It was always poised on the edge of changing, and the right microscopic event simply gave the transformation a place to begin. Now, the second trigger people love to imagine is dramatic. A collision between universes in a multiverse. If our universe were one bubble among many, each bubble could correspond to a different vacuum state, a different set of low-level parameters, a different way for fields to settle. In such scenarios, a neighboring bubble expanding through the larger cosmic environment might someday intersect ours. At the boundary, the physics would not politely negotiate. One vacuum state would replace another, and the result for anything built under the old rules would be catastrophic or, depending on your taste for metaphors, transcendent. The difficulty is not in telling the story. The difficulty is in testing it. Multiverse collisions are speculative, and the distance between possible in equations and detectable in reality can be vast. Still, the idea matters because it forces a deeper question. Are the laws we measure properties of the universe, or properties of the vacuum state our universe inhabits? And that brings us, naturally, to the most human fear of all. Could we trigger vacuum decay ourselves? Could an accelerator, a powerful laser, a future technology we cannot yet name, poke the vacuum hard enough to knock it into a new phase? This question has hovered around particle physics for decades, not because scientists are reckless, but because the stakes of the hypothetical are so absolute that even a vanishing probability feels emotionally loud. The comforting answer, based on what we know today, is that human technology appears nowhere near the energy scales that would be relevant. Nature runs particle accelerators far more powerful than anything we have built. Cosmic rays slam into atmospheres and surfaces across the universe at energies that dwarf our machines, and they have been doing so for billions of years. If those events could easily trigger a vacuum transition, the universe would have had ample opportunity to do it already. This is one of those rare moments when the brutality of nature becomes our reassurance. The cosmos has been stress-testing itself long before we arrived with magnets and ambition. Still, there is a subtle lesson hidden in the worry. It is not really about whether a laboratory can end the universe. It is about how close our understanding is to the bedrock. When you ask whether technology could trigger vacuum decay, you are also asking whether the vacuum is a fragile arrangement balanced on a knife edge, or a robust foundation with margins of safety we have not fully mapped. Here is a second example, far from the first, to make the idea feel less abstract. Imagine a valley covered in fresh snow, smooth and serene. the kind of silence that makes you whisper without realizing it. High above, the slope looks stable, but buried within the layers is a weak seam, invisible from the surface. Most days, nothing happens. Then a small change in stress, a vibration, a shift of temperature, and the entire mountainside reorganizes in one sweeping motion. The snow does not vanish into nothing. It becomes something else, a new arrangement, a new geometry, a new reality for anything caught within it. In the vacuum decay story, the avalanche is not matter sliding downhill. It is the rules themselves changing their resting place. And this is why the question of triggers is more than a spooky thought experiment. It is a way of learning what stability means in fundamental physics. It forces us to connect the smallest measurements, the properties of fields, the masses of particles, the shape of an energy landscape, to the biggest possible outcome, the long-term fate of everything. It also teaches a kind of scientific humility, because the universe we inhabit feels inevitable only because it has lasted long enough for us to be born inside it. But longevity is not the same as permanence. A bridge can stand for centuries and still be the product of stresses you do not notice until you measure them. So what can trigger vacuum decay? In principle, it could be a spontaneous quantum event. In more speculative frameworks, it could be influenced by a collision with a different vacuum region, perhaps another universe bubble. And in the realm of human technology, the best evidence we have suggests we are not even close to the energies that would matter, while nature has already performed far harsher experiments without consequence. Yet the most important outcome of asking is not fear, it is clarity. Because the vacuum, the thing we casually call empty, may be the most active ingredient in the cosmic recipe. And if you want to understand what could ever rewrite the universe, you first have to understand what the universe is truly resting on. So stay with me, because the next step is to look at the evidence trail that leads physicists to even take metastability seriously, and why two seemingly modest numbers in particle physics can whisper a story about the ultimate durability of reality itself. What if the universe did not begin with creation, but with collapse? What if the moment we call the Big Bang was not a birth, but the quiet aftermath of something that ended before us? This question has haunted modern cosmology for decades, because hidden beneath the equations of quantum fields lies a possibility both unsettling and strangely elegant. The idea that vacuum decay may have already happened, long before stars, before atoms, before time itself felt familiar. In the earliest instance of cosmic history, during the phase we call inflation, the universe expanded at an almost inconceivable rate. Space itself stretched faster than light could travel, smoothing irregularities, erasing structure, and laying down the seeds of everything we see today. But inflation is not just rapid expansion. It is intimately tied to the energy state of the vacuum itself. Many physicists believe inflation was driven by a high-energy vacuum that later transitioned into a lower-energy state. In other words, a vacuum transition, a change of phase, a fall from one energetic plateau to another. Alan Guth once described inflation as the ultimate free lunch, because it creates matter and structure from the energy of empty space itself. That statement carries more weight than it first appears. If inflation was powered by a decaying vacuum, then our universe may literally be the residue of an earlier, unstable state of reality. Not built from nothing, but formed from a collapse into something more stable. Imagine a mountain landscape hidden beneath thick fog. A marble rests in a shallow depression and appears perfectly still, yet far below lies a deeper valley the marble has not yet reached. If, through quantum chance, It slips and falls. The entire landscape of motion changes. Inflation may have been that fall, the moment when a false vacuum gave way, releasing energy that became space, time, and matter. In this view, the Big Bang is not the beginning of everything, but the boundary between two phases of existence. This idea grows even more provocative when we ask whether vacuum decay could ever be observed if it happened again. The unsettling answer is likely no. A true vacuum bubble would expand at the speed of light, rewriting physical laws as it passes. No warning could outrun it. No signal could arrive ahead of the front. By the time information reached an observer, the observer would already be gone. Reality would be replaced before it could be noticed. Consider a second image, far removed from the cosmos. Imagine living inside a perfectly calm soap bubble, floating in still air. From the inside, the surface feels solid, eternal, unquestionable. Yet the moment the bubble touches a needle, there is no sound, no warning, no transition. The bubble does not feel itself pop. It simply is not there anymore. A vacuum decay would be similar, except the bubble is the universe, and the needle is a fluctuation written into the deepest rules of nature. This absence of warning tells us something profound about the limits of human perception. We are accustomed to disasters that announce themselves. Earthquakes rumble, stars explode in light. But vacuum decay, if it occurs, is not violent in a way our senses can register. It is silent, instantaneous, and absolute. It reminds us that the most consequential events in the universe may be the ones that leave no trace behind. Yet the story does not end in fear, because the same idea that allows vacuum decay also explains why our universe exists at all. The measurements of the Higgs field suggest that our vacuum sits precariously close to the boundary between stability and instability, not falling, but not deeply settled either. Some physicists see this not as danger, but as a clue. As Steven Weinberg once remarked, the more the universe seems comprehensible, the more it also seems pointless. His S. I'm not fellow 8. And yet, here comprehension emerges precisely from fragility, from balance, from conditions tuned just enough to allow structure, stars, chemistry, and thought. If vacuum decay happened in the past, then we are living proof that collapse can be creative. That destruction at one level can be the foundation of order at another. Our atoms, our galaxies, even our thoughts may be echoes of an ancient transition in the fabric of the vacuum itself, a reminder that reality is not static, but evolutionary, capable of changing its own rules. And perhaps that is the deepest lesson hidden in these questions. Not whether the vacuum can destroy the universe, but whether destruction and creation are ever truly separate. If we are living in the aftermath of a cosmic transition, then existence itself is a survivor of instability, a fragile flame balanced between what was and what could be. So when we ask whether vacuum decay could happen again, we are really asking something more intimate. How stable is the ground beneath our certainty? How much of what we call reality is permanent, and how much is simply holding together for now? And as we turn to the next part of this journey, we must begin even deeper by confronting the simplest question of all. Is the universe truly full, or is it mostly made of emptiness, waiting, silently, beneath everything we know? What if the laws of physics are not commandments carved into stone, but simply the habits of the universe, learned over time and subject to change? We grow up trusting that gravity will always pull, that light will always race at its familiar speed, that atoms will always bind the same way, and that tomorrow will be built from the same rules as today. But the deeper we look into the foundations of reality, the more that certainty begins to feel like a comforting story we tell ourselves in the dark. Because physics, at its most honest, is not a list of eternal promises. It is a description of patterns we have measured so far, within a cosmic moment that may be only one chapter in a much larger book. There is a line often credited to Albert Einstein that feels unreasonably relevant here. The most incomprehensible thing about the universe is that it is comprehensible. Seamless. That single sentence carries both wonder and warning. Wonder, because the universe allows itself to be read. Warning, because what we can read may depend on where we are in the story and which page we have been allowed to see. When we ask whether the laws of physics are immutable, we are really asking something far more intimate. Are we living inside a reality that is fixed forever, or inside a reality that is stable only for now? And if it is only for now, what does now even mean on a cosmic clock? In modern physics, the vacuum is not an empty stage where the universe performs. It is more like the stage itself, alive with tension, structure, and possibility. And if the vacuum can exist in different states, then the rules that emerge from it may differ as well. Not because the universe is careless, but because different ground states can produce different kinds of matter, different strengths of forces, different possibilities for chemistry, and therefore different possibilities for worlds. This is where natural constants enter the conversation like quiet monarchs. The masses of particles, the strengths of forces, the way space expands, the value of the vacuum energy. We call them constants because they appear constant in our measurements, but the name is not proof of permanence. It is a reflection of what we have observed within the narrow corridor of time and space available to us. And the unsettling question is not only whether they could vary in principle, but whether they ever have, or could in some distant region beyond our view. Imagine, for a moment, a violin string pulled tight. As long as the tension is steady, the note remains stable. But if the tension shifts, even slightly, the note changes, and a whole melody can become unrecognizable. In the same way, the laws we experience may be the audible notes produced by deeper tensions in fields that fill space. If the underlying tension changes, the music changes. And in a universe with multiple possible vacuum states, it is not absurd to wonder whether different regions could play different songs. Here is one example to make that feel less abstract. Think about water. At everyday temperatures, it is liquid, flowing, familiar, life-giving. But the laws of water's behavior shift drastically when it freezes into ice or boils into vapor. The molecules have not changed their identity, but the state has changed, and with it the rules of structure and motion. Now stretch that idea to the fabric of reality itself. If the vacuum is like the phase of the universe, then a shift of vacuum state would be like a cosmic phase transition. Same existence, different operating system. And suddenly the question, are laws eternal, becomes, are we mistaking a stable phase for an eternal truth? Too friend. The idea that physical law might be contingent does not weaken science. It sharpens it, because it forces us to separate what is deeply necessary from what might be historically accidental. It also forces humility into the heart of knowledge. We are not outside the universe reading a manual. We are inside it, trying to infer the manual from the way the machinery behaves around us. And it may be that the machinery behaves this way not because it must, but because it currently does. That brings us, naturally, into the philosophical weight of an unstable universe. If reality can change instantly, what is the meaning of existence? This question sounds like poetry, but it is anchored in physics. In some theoretical pictures, a change in the vacuum would not be a dramatic explosion that lights up the sky. It would be a quiet rewriting, a new set of constants, a new set of stable particles, or perhaps no stable particles at all, a new chemistry, or none, a universe that continues, but not in a form that recognizes us. And that realization flips a switch in the human mind, because we usually think we are living in a home built from permanent materials. But what if we are living in a home built from conditions that merely hold? What if the walls are not stone, but frozen wind, still strong enough to shelter us, yet dependent on a deeper temperature we do not control? Later, consider a second example, far from water and closer to the heart of matter. Imagine if the strength of the electromagnetic force were slightly different. Not by a dramatic factor, but by a whisper. The sizes of atoms would shift. Chemical bonds would change their character. The periodic table would no longer be the same map of possibilities. Stars might burn differently or fail to ignite in the familiar way. Life, if it emerged at all, might be built from unfamiliar scaffolding, or might be impossible. In that sense, the laws are not just equations on a blackboard. They are the permissions that make complexity possible. They are the quiet agreements that allow atoms to become molecules, molecules to become cells, cells to become memory. So are we the masters of the universe, or merely passengers? Everything we have ever achieved suggests mastery in a local sense. We shape landscapes, split atoms, send instruments into deep space, and write mathematics that predicts the turning of galaxies. But mastery is not authorship. We did not choose the constants. We did not decide the vacuum state. We did not negotiate the strength of gravity or the charge of the electron. We arrived mid-story, breathing air that only exists because deeper rules currently permit it. That does not make us powerless. It makes our existence astonishing. And then comes the most haunting inversion of all. Is the vacuum a destroyer, or the cradle of every possible reality? If it can decay, it can end our version of the universe. But if it can shift, it can also begin other versions, not as fantasy, but as a legitimate implication of fields and states and energy landscapes. In that light, the vacuum is not merely emptiness. It is the womb of law. It is the hidden source from which the rules of matter and light are born. Perhaps the deepest educational gift in this entire idea is not fear, but perspective. We learn that stability is not the same as eternity. Bomb, I-team. We learn that constant is a word that may reflect the limits of our measurement rather than the limits of nature. And we learn that knowledge is not a fortress, but a lighthouse. It illuminates what it can, while admitting the ocean beyond. So here is the question I want to leave echoing in your mind as we move forward. If the laws of physics are the voice of a particular vacuum state, and if vacuum states can differ, then what, exactly, are we calling reality? End of next. And in a universe that may be stable only for now, are we here to conquer it, or to understand the miracle of riding it while it lasts?